All right, class, this section is 3.3 and we're doing, they call it measures of relative standing and box plots. So this first relative standing idea is Z-score. And the Z-score or standard score or standardized value is a number of standard deviations you are away from the mean. So again, it's the number of standard deviations you are away from the mean. Okay, so if I'm one standard deviation away, that's not too bad. But if I become 2 standard deviations away from the mean, then I'm pretty much an outlier or pretty close. 3 standard deviations, you're definitely an outlier. This is often on an IQ exam. So it's like, how many standard deviations are you away from everybody else? The way that we compute the z-value is we take whatever value we are, our data value, and we subtract off the mean, that's giving you how far you are away from the mean, and divide that by the standard deviation. Okay, so this is what we'll mostly see with the sample. Same notation, same idea with population. So the value minus the mean divided by the standard deviation, but that's of the population. Okay, so the properties, a z-score is the number of standard deviations that a given value x is above or below the mean. So it's telling you something about a specific data value. Where are you on the IQ exam? Or where are you compared to everyone else on anything? So the z-scores are expressed as numbers with no units of measure. There's no unit. It's how far you are away, how many standard deviations you are from the mean. It's not like it's going to be length and, centimeters or anything. A data value is significantly low if the z-score is less than or equal to -2, or the value is significantly high if the z-score is greater than or equal to 2. So at that 2, now you're 2 standard deviations away. That's a lot. If an individual data value is less than the mean, its corresponding z-value is negative. I don't know why this is way down here on my notes, but it is. So I'm going to show this before I do the example. So here's 0. If you're at 0, you're at the mean. Like, you just average. You're right in there with everyone else. If you're at 1 or -1 or lower, right? You could be 0.2 or something like that. You're in, the values are, it's not very significant. You're right in there with everyone else. But I hit the 2 and we become significant. I hit the 3 and I'm definitely significant. So let's try this example here. Which of the following 2 data values is more extreme relative to the data set from which it came from? So the 4,000 weight of a newborn baby, 4,000 grams, among 400 weights with the sample mean of this and the sample standard deviation of this. So we're going to find the z-score of this 4,000. So I take my value, my x value, 4,000, and I subtract off the mean, 3152.0, and I divide by 693.4. Okay, so let me grab my calculator. 4,000 minus 3152 is 848 divided by 693.4. 693.4. I get 1.22. So about 1 standard deviation, 1.2 standard deviations away from the mean. Okay. Let's look at this next one. Now I kind of have my work still there from the first one. Sorry, just the way I did it. Maybe I'll just move this paper over. Flip it over, use the other side. So the 99 degrees Fahrenheit temperature of an adult among 106 adults with the sample mean and the sample standard deviation. So is this an extreme? We know the other one wasn't really extreme because 1.22 is still less than 2, so it's pretty average. Okay, so this one I'm going to do 99 is my value, subtract off 98.2, and divide it by 0.62. This is a good one with all these temperatures we've been taking for COVID. Like, what if yours is a little off? I'm lucky because mine is extremely low temperature, so mine's not high. I don't know if that makes me lucky. It just is what it is. So I get 0.8 divided by 0.62. And I get about the same, 1.29 or 1.3 is how many standard deviations you are. So this one's not extreme either. But you see how to calculate that Z-score. And it's a great way to see where is somebody compared to everybody else. Okay. So we have our significant. If you want this same note sheet, it is in Canvas or it's in the lecture section where I didn't post them at first. Now they are. It is in the lecture section of my math lab. I just started doing that. Okay, so here is what we call the standard normal curve, right? We have that bell shape. We've been talking about it a bunch. At the zero, at the middle, our Z-score is 0, okay? And our mean is what is at the middle, right? So this represents the mean at the middle. And our cumulative percent is it represents 50% people below it or above. And we start to have different percentages in here. This will become handy as we compare and look at different things. So just keep that in mind. I added that for you. I got that off the internet. So the lowest platelet count in a data set is 75. Counts are measured in 1,000, whatever. Okay. Is that value significantly low? Assume the platelet counts have a mean of this and a mean of this. So I have one more Z-score example here. So my Z is going to be 75 minus my mean of 239.4. Divide that by 64.2. Standard deviation. That looks way low. It's not part of this. This is just for you to have. And it will be pretty handy eventually as well. So 75 minus 39.4. And I'm going to divide that by 64.2. I didn't show all my middle steps. So that's about negative 2.56. So there's our first example of one that's extreme. It's actually our third example, but whatever. The other ones were one example, I guess. So our extreme, that one is way extreme. And look at it, mean, our value. Clearly we're way lower, okay? And we can use that Z-score to compare. So a person with a Z-score of a negative 2.6 is way over here, and you can see overall cumulative to percent, less than 1% is in that area. You are definitely way off the normal. Okay, percentiles. When I say this goes along with it. If I say you are in the 90th percentile for my class grade, what am I saying about you? I'm saying 90% of the people are below you, right? You are right there at 90%. So you're way up on the category. This is a different way to look at the same thing. It's not a Z-score, but it's kind of telling you that same idea. Where are you with those percentiles? So percentiles are measured and are denoted by P1, P2. So like P1 is 1%, P99 is 99%, which divide a set into 100 groups. So you're breaking something up into 100, and each group is 1%. So percentiles. The process of finding the percentile is it's the number of values less than you are, or the data value you're looking at, divided by the total number of values, and then you times it by 100 because that gives you the decimal. Times it by 100, now you have the percent. So let's bounce. I think I still have this exact problem. Did I close it? I did. Let me show an example of this from the homework. So 3.3, let me open this. So I'm going to stop share, and I have to share my screen differently. Okay, and bring bring over my face. Bring over this example here. Not this one. Oh, it's like, I don't remember which problem. I had it open, obviously I closed it. No, we're not to that yet. Nope, we're not on Q1 yet. Oh. What percentile is 1.4? So we have all these data, and we want to know the percentile of 4.9, not 1.4, whatever. 4.9, I don't know where 1.4 came from. Here is that data value. So what I would do is open this up in Statcrunch, and your data should be in order, which it is for you. And we're going to just scroll down. It's already in order. You can put it in order in here. We've gone through that before. It's in the sort data sort. So if you want to put it in order, and we can look, here's our 4.9. So 32 values below it. So we're going to do 32 values. So I'm going to write this down in on my paper here. So 32 divided by, oh, how many values were there? I think I closed Statcrunch. How many values were there total? 50. So 32 divided by 50 and times that by 100. So I'm going to get out my calculator. 32 divided by 50 is 64. So this should be the 64th percentile. Ta-da! That's how you do a percentile of where something is. Okay. All right. Oh shoot, and then I showed one. I wanted to, this one's more for my in class. If you look at this note sheet, it's like the same question we just did. Refer to the sorted data speeds, a question above. Find the 40th percentile denoted by P40. So 40th percentile denoted by P40. So if we're looking for the 40th percentile, then we're looking for exactly where something is. So the easiest way is to probably add up how many total. Did I show that one? Oh, I did. I was like, I don't think I have it. So I was going to open up the example again because I was like, oh, I don't have a good way to show this one. So we can, I showed the work because I think you need it. We can proceed by computing the value L. So we're trying to figure out which number is the 40th percentile. So we have 50 numbers in my example above, and there's 50 data values. So you're thinking, what number divided by 100 times n's going to be our 50, is going to equal, or where would we be? So we would take and try to figure this out. So we can figure it out as the 40th percentile out of the 100 times by the 50 would give me 20 numbers in. So we can see that the 20th number, that next value, would give us that 21st. So the 40th percentile is midway between the 20th and the 21st value. Ooh, it's midway between the 20th and the 21st value because it's the 20th number along. So I'm going to go up here and I'm going to count 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's 20. So it's midway between these two. That's a little tricky. It's the halfway between those two values. So I got the 20 by just basically looking at the same way we calculated it. The 40 divided by the 100 times by the 50, the n value. So the 40th percentile number is 11.7. Okay, so I kind of worked that out for you and wrote it out. I totally think that one's tricky. That's why I wrote it out on here. All right, so let's go into our box plot and we finding our quartiles. This is something you've done before. Whether you took Math 1000 or maybe 1400 doesn't have it. quartiles. What's a quartile? It's like breaking something into 4 pieces. So I take my data, I break it in half, and then I see what's half of the top half, what's half of the bottom half. So we're finding the median of the whole thing, the median of the top, and the median of the lower half, and those are our quartiles. That's it. Okay, first quartile is the same as the 20th percentile, same thing. So sometimes you have to add 2 and divide it by 2 to get the average, just like our median. It separates the bottom 25% and the top 75%. Okay, so that's our quartile. 2 is the same as the median. And then our quartile 3 is that 75%. It is the median of the top half. Okay, so these are interquartile range, semi-interquartile range. These are just a mid-quartile range, other statistical things that use quartiles and percentiles. And I really just want to bring your attention to the IQR. That is the difference, subtracting your upper and lower quartiles. So you have the median of the upper half, median of the lower half, you subtract those, okay? It's another, interquartile range is another way to find whether something's extreme. So we do refer to that sometimes. All right, so when we go to do our box plot, we do what's called the 5-number summary. We do the lowest number, that first quartile, the highest, or the median, excuse me, the third quartile, and the highest number. So we're basically taking the lower number, the highest number, the median, median, median. That's our 5-number summary. We just broke our data into 4 pieces. Yes, you need 5 numbers to break something into 4 pieces. So you need the top and the lower. Okay, so I'm going to show this in Statcrunch. And I do show the solution for right below it. I do write out in a solution if you want to see one. Okay, so let me show this in Statcrunch. So I am going to just use that same data we were just looking at. Oops, I got to stop share. All right, and then I want to share again, but not my thing. Okay, so here's that same data, totally different problem, but this data will be perfect. So we're going to go ahead and go to stat and summary stats, okay, of a column. And this is where we can get all these values. So I'm going to unclick, oops, I want to click one variable. I want it of this first row, and I'm going to scroll down. I do want the median. Okay, I want the low, oops, median. Push Control Shift, and you can do, or just Control, because Control will let you pick what you want. Min, max, okay, quartile 1, quartile 3, median is quartile 2, and 1, 2, 3, 4, 5, compute. All right, there is, of our variable 1, there's our values that we want, our minimum, our max, and our other quartiles. So again, this is called our 5-number summary. So I'm going to write these in the order which we usually see them, which would be 0.1 is our min, and then our quartile 0.7, Q1, and you'll see my writing in just a second. Our median is 2.9, and that's also Q2. If you do it on your graphing calculator, it will call it Q2. Q3 is 17.3, and our max was 27.4. Okay. All right, so I wrote down those values that you could get from Statcrunch in summary stats of your column. So then what I'm going to do is I'm going to show you what a box plot is going to look like. Sometimes they call it box and whisker. First, I start with the number line, and this data definitely is close to 0. So I'm going to start at 0, and I'm going to count to 30 because the values go to 27.4. So maybe hopefully 5, 10, 15, 20, 25. Nope, let's do more. 10, 20. All right. Those don't look that great. Should have drawn this out before. That's right. 10, 20, 30. Let's do this one just a little over. Yes, I'm being picky. Okay, so 10, 20, 30, just like that. Then we'll just guess about where these dots are. So we put our 5 dots on there. So 0.1's barely over 0. 0.7 is barely over 0. And I had to separate them. I know that's not quite right. And then 2.9 is still like right here. And then 17.3, here's about 15. So 16, 17, and then almost to 30. So we're going to draw a little, a line down the median. This is going to be a line. So that was at 2.9. So I do a line down the median and a line down the next ones, and I draw the box. So this is going to be our Q1. This is our Q3, and our Q2 or our median. Those form our box, and our whiskers will go out to the lower or the higher numbers. All right, so that's our box and whisker plot or box plot. It shows that the data is way more spread out at the top because those quartiles are really long and spread out, whereas the data down here is really close to the same numbers. So it's showing you how spread out your data is in each category. Because remember, this 1, 2, 3, 4, I broke your data into 4 pieces. Each piece has the same number of data. But if it's closer together, then those datas are almost the same value. Okay? So that's our box plot. And one other idea, I do want to come up with a couple things. It does show skewness. You can see how skewed a data is, like our data. Our tail, let me think about that. Our tail is going to the right, so it is right skewed. I had to think about whether the tail would be on the left or the right. Okay, so a box plot can often identify that the distribution is not symmetric. So basically our data was not symmetric. It does show our distribution way clumped more and then way more spread out. This one is not as spread out. Maybe this section here is more spread out. Maybe you have an outlier at the top. How do I identify an official outlier? What I'm going to do is I'm going to find the IQR, the interquartile range, by Q3 minus Q1, okay? And then I'm going to times that value by 1.5. Anything above or below that value is a outlier. So a modified Boxplot is oh well, anyway, that's how I evaluate an outlier officially. So a lot of times we just look at it and go, yeah, that number is probably an outlier. This is an official way, 1.5 times the IQR. If I use a modified box plot, a data value is an outlier if it is above the Q3 by the amount greater than 1.5 times the IQR or below Q1 by the amount of this. I don't understand the modified box plot word in that one, but basically we're just looking at whether it's an outlier. So a modified box plot is basically where you use an asterisk for your outliers. Let me see if this one that we just were doing the value for, I want to see if this one has one. So basically we're going to ignore our box plots, the outliers. This data I bet had an outlier. So box plot compute. Nope, it doesn't show an outlier. So let me go in here. I'm going to close that. I'm going to go down here and make an outlier. So what would be an outlier? Way off 27, 200. Okay, so now I'm going to go to Boxplot. I want to show you the modified Boxplot. Ta-da, there it is. This is a modified Boxplot. It basically took this value and said that is way off, and it made a box plot with the rest. And this is a good way to find out if something is officially an outlier, is I make a box plot. If it's a dot way off, they use an asterisk when you draw it by hand, then it was an outlier. Okay, so this section, we're looking at Z-score to see how far away from everybody else you are. We can look at a Z-score. Okay, and we found that by subtracting your data off of the mean and dividing it by the standard deviation. And it was how far you are away from a standard deviation, or how many, excuse me, standard deviations you are away. Then we looked at our percentiles, same kind of idea. Where am I compared to everyone else? So percentiles you could find by the number of values below where you're at divided by the total number of values times by 100 to make it a percent. Then we looked at our 5-number summary, okay, and we found the box plot, which also shows how spread out your data is in each section. And basically we found a median, 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 high, low number. Okay, we can do that in Statcrunch as well. And we found that we can find the official, if something is an outlier, using IQR times by 1.5. All right, or we can just plug it into Statcrunch and see if it makes a little dot way above your box plot, and it did it for you.